So I'm going to talk about stuff which is should be of interest to deep learning in the sense that optimization of a certain type comes up a lot. And the optimization is tied together with sparsity. So I will actually talk a lot about compressed sensing and algorithms to solve problems involving sparsity and where it fits in the learning business. So I'm starting out with this quad chart, which is just advertising for the Navy, which is, gives a little overview of what we can talk about. The idea is to improve the accuracy and applicability of L1 type stuff, things related to L1. And there's something called Bregman Distance, which was mentioned by Stephen Wright, which is going to play a big role in lots of the algorithms. And it turns out this stuff is extremely useful for L1, and L1 is extremely useful for sparsity, and sparsity is extremely useful for deep learning, it appears. So that's what I'm going to talk about, and here are some of the applications. Let me start out by showing. So what you see in the upper left is a parking lot of an Army base, would you believe? And we took a video and removed about 60% of the data randomly. And then the goal was to find moving objects without any a priori knowledge. And the key idea here is that this video can be viewed as a three-dimensional object, space plus time, and you decompose it into low rank plus sparse. Low rank plus sparse. And the low rank part is all those cars that sit there. They don't change over time. So as time progresses, the rank of that stuff is essentially 0. And here you see the people walking over there, and that's sparse. And that's hard to see. You beat the human eye, actually. In there, what you see on the upper right is the difference of two frames. The original over there, it's hard to find these two people roaming around, but we can find them pretty easily with this decomposition, and this decomposition involves some kind of compressive sensing type idea involving sparsity and low rank, which is very much related. I may come back to this with more equations, but let me give you a little overview of new ideas in imaging, many of which are related to this. New algorithms in image science, and this is about a year and a half old talk, so there's newer stuff. But I think for this audience, it's supposed to be a tutorial, so it's not bad to review a little bit. There's lots of people here, many of whom are no older than you are, who are students and whatnot. Okay. So what we're actually talking about is revived and improved. Nothing is ever new. I have found over the years the most important thing is to be the last person to discover something. Then you really get famous. Most things have precedence. So for example, an idea here is called Nonlocal Means, which has led to dictionary learning. And the idea is based on redundancy in images. So if I look at you guys, I see lots of heads. You're all unique individuals, but nevertheless, the heads and hair and faces and noses have things in common. There's lots and lots of redundancy in what I'm looking at right now. So to essentially reconstruct an image, you can take a few patches of the image itself and use them, even if they're noisy, to remove noise all over the place and reconstruct. So this idea of non-local means has led to dictionary learning, and it basically means averaging over image space. And I'll give you equations in a minute. And it's been a terrific success. Okay. And then even more hype and success is associated with compressive sensing. It was done basically at UCLA by Candes and Tao, although if you look carefully, you'll find Galileo more or less knew it. Basically, the idea was that L1 will give you sparse recovery, and all this stuff turns into equations very soon. Next, we have fast optimization algorithms using for L1 type problems, which I've been involved in. And then I'm not going to have time to go into it, but historically there's differential equation variational methods for image processing and level set method, which I love, but it's a little far afield, so maybe I won't go into it. So here's a crucial diagram. I haven't been to many lectures this week. I blush to admit I've been traveling. So has this diagram appeared before? No. Ah, God, what do they teach you around here? Okay, sorry about that. This explains why L1 implies L0. This is really important. What does it mean L1 implies L0? You have an equation AX equals F. Okay, I have to shout. Here's AU equals F. This is one equation in two unknowns. So there are many, many solutions. Anything that lies on that line is a solution. What you want is a solution which has the fewest non-zero elements, right? That's called Sparsit Solution. So U is a 2, in this particular case, U is a 2 vector. In general, U is an n vector, and in fact, for deep learning, n is 5, is many dimensions. But the idea is just the two-dimensional problem, and it generalizes. So for this two-dimensional problem, you want to minimize, if you minimize the L1 norm, what's the L1 norm? Okay, the L1 norm is the sum of the absolute values of the components, right? Not squared, but to the first power. That shouldn't be such a remote concept. And the L1 unit ball is a diamond, not a sphere. It's a diamond, right? Because that's x plus y. This is x plus y equals constant, x minus y equals constant, and whatever. Minus y minus x, and so on. So that's a diamond. And now what you're looking at is minimizing the size of the diamond, the L1 norm of U, such that AU equals F. And what you're doing is looking for the intersection of when you expand this diamond out where it hits this line. And the probability is 1 that it will hit it on an axis, right? Okay. You should be nodding sagely. It's going to hit it on an axis. It's not going to hit it in the middle over here where there are two non-zeros. It's going to hit it over there where there's one non-zero. And that has caused a revolution in signal processing and information theory and all on. This baby idea that the L1 norm, which is a convex function, will give you the Sparsit solution. Of course, this is just one trivial example, and there's no guarantee that it's going to work in general, but it does. Almost. You need some theorems, of course, about A and so on. But that's the basic idea. You can get the Sparsit solution by minimizing the L1 norm, and that's a convex function. And therefore, you can do it in a reasonable way. If you minimize sparsity itself, that's an NP-complete problem, very hard to do. I can't do it, actually, in a finite number of steps in principle, but L1 you can do, and we do it great around here. And that's what you're going to hear about. Okay, so any questions about that? This baby little problem. And the same thing is true in much higher dimensions. You're going to hit it on axes. For example, if you were dumb enough to do L2, which we're not allowed to do in the zip code, you would probability 1, the L2 unit ball is a sphere, a circle, right? So the chances that you will hit it on an axis is probability 0. It has to be vertical or horizontal. But you're going to hit it somewhere where there are two non-zero quantities, and which is not sparse, as dense as possible. And you can do it, you can generalize this a little further. I mean, here's a stupid example, but it's fun. Take one equation and 10 to the third and 10 to the fourth unknowns or something. AX equals F, very underdetermined problem. And you would like the Sparsit solution. Well, of course, the Sparsit solution would be anything. Any UI is equal to F divided by AI. Everything else is 0. That's sparse. But, it's not unique. But anyway, there's lots of possibilities. But if you take the L1 minimum and suppose one of these AKs is the biggest, then you can write down the answer. And it turns out to be U is 0, 0, 0, F divided by AK 0, 0, 0, 0. So it's sparse. So the L1 minimum gives you a sparse solution. And the L2 minimum, God forbid, gives you a dense solution. The densest possible, practically. It's a multiple of A. So L1 good, L2 bad for this business. And Gauss ruined everything. And so what we're going to talk about is what you do with this and how you solve it. Any questions about this? Very basic notion. Non-local means, I mean, this also ties in with dictionary learning and stuff that you heard about. It's an idea which was introduced by these guys, But again, nothing is really original. It was floating around. You have an image which is u of x, and you want to basically filter it. In the old days, you would filter it by taking the average of u in some neighborhood of a point. In these new days, you filter it by taking the average of its u values. You look for similar patches of u values, and you average those out. That's what that formula tells you. And this I won't go into in as much detail as the other stuff, but it has led to unbelievable denoising, absolutely incredible denoising, and lots of other tasks. And it has also is very much related to dictionaries because you get these patches and you match other patches to them. So this is a nice idea. And you can make, I'm going to get back to this later, you can make calculus out of it with machine learning, and that I'll do later. And I'll just show you some pictures real fast. Here is denoising a surface. This is an idiotic surface. I mean, the original surface is just a clean version of this. This is what you used to get with the old stuff that I did, and this is what you get now, or the 5 years ago. You can do even better, just by taking patches and averaging them. Same thing with this kind of stuff. This is last year's or last decade's idea. This is what you get now. And you can get better results, amazing results, just by doing this kind of averaging. And maybe in the second part of today's lecture, I'll talk about this in detail. Here's the original. And here's some, it's hard to see, but here are some noisy brain images. And the idea is to remove noise without killing the data. And this stuff works well. You can see on the right versus left. Okay. And this comes from, and that came from our local brain imaging center. And here is some stuff from National Geospatial Agency. This is noisy data. This is what you, first you pass the surface through it, and this is what you get now. And this does a very good job of denoising. So I will get back to this later, probably. And it's very much related to dictionaries. Okay. And I'll skip this stuff for the moment and go on to this. Okay, so how does this all fit in with what you're interested in, which is deep learning? Well, this gives you fast ways of solving these problems, and sparsity is associated with these neural net problems these days. So here's a nice application, MR images. You need fast MR image acquisition because, for example, when a beating heart causes artifacts, or imaging kids, it's hard to keep them still, or imaging grown-ups or old people like me. If you lie there, it's very unpleasant, and it's hard to sit still. And this allows you to do it with less time, in less time. And this is, again, this is like 4 or 5 years old. If you type in MRI total variation or MRI compressed sensing or something, you'll get about 200 papers now. So this stuff has taken over very quickly. Okay. But anyway, you can imagine applications. Breathing motion causes artifacts and so on. If you sit in an MR machine, it's very unpleasant, and you want to get it done as fast as possible. So this enables you to do it faster, this being compressed sensing. So acquisition time. In MRI, you don't directly acquire the images. You actually take the Fourier transform of something, basically. So think about it that way. You have an image, and you basically take its discrete Fourier transform, and then you sample it, or compute every single point of the Fourier transform, and then try to recover what was there originally. But the idea would be to use less data. And that's where compressed sensing comes in. And this is where compressed sensing actually started. There's a paper by Candes in which he applied total variation to an MR image and found that you get, by minimizing TV, you only need about 30% of the data to get the exact answer. There is something called the Nyquist criterion. Have you guys heard about that? You don't need it. The Nyquist criterion says you need as many samples as there are Fourier coefficients, or twice as many if it's complex. And you do if you want every piece of data, but typically you don't need every piece of data because there's not much data. And you have things which are piecewise constant or have a little bit of structure. And only a few samples can give you the right answer. And that's what compressive sensing tells you. So let's talk about that. Suppose you want to construct a 1 megapixel image. Conventionally, you would take 1 million measurements. And then you might compress it or something. But why do you need 1 million measurements if only 1,000 pieces are needed to represent the image if you store it? Images are smooth. There's lots of redundancy. So if you know that the set of signals represents a smooth image, then you can use the information to reconstruct the image from a small number of measurements. And this is really a big deal. And again, this is not pie in the sky. This is going to be FDA approved one of these days. I mean, it's very, very on top of things. It actually works. Okay. So you need the measurements to be taken in a special way. Here we go. Compressed sensing. Compressed sensing techniques construct high-resolution images from a small number of measurements. If you do it right, then you only need a small data set and you get the exact answer. That's a lot to ask if you have noise and stuff. So generally, you get close to it. But the theorem of Candes and Tau, which under some circumstances says that you get the exact answer by if the data you're looking for has like k non-zero elements, and you take about it depends on many parameters, but typically about 3 times as many measurements as there are non-zero quantities is about all you need to get the right answer. Okay. So to do this, you have to take a transform. And the basic idea, again, I can say in words, is very simple. If you have a single spike, a single piece of data, and you take its Fourier transform, what you get is all over the place. It's an exponential, e to the I x dot c times a constant. So the only thing unknown is the location of the spike and the magnitude, two quantities. And by sampling the Fourier transform, you obviously, a few samples, you could do it if you knew it was only one spike. This says you don't have to know how many it is. And there's an algorithm for getting the answer, which is quite general. And that's what this stuff is about. And the theorem goes back to, the theorem is due to Candes and Tau, but Donahoe had a lot of interesting ideas before this, and many, many people sort of knew that this was true, but these guys made a big deal about it and proved a nice theorem and realized how important it was. And it's really taken over. Okay, so for this MRI applications, you don't acquire the images, you acquire the k-space data. And the actual image is reconstructing by taking the Fourier transform of the k-space data. With compressive sensing, you can reconstruct a high-quality image from a fraction of the k-space data. So you can do image acquisition 3 to 5 times faster, which is fantastic. If you're lying in this horrible machine, which is noisy as hell and expensive and unpleasant. Yep.
What is the k-space?
Fourier transform. Think about Fourier transform. Let's think about Fourier transform. This is medical mumbo jumbo or whatever it is, physics stuff, which I don't want to go into. But the basic mathematics is you're taking a discrete Fourier transform of a more or less piecewise smooth object. That's what it amounts to. Yeah. But your question is a good one. I didn't answer it. Sorry. Okay. Yeah.
Does this require some adjustment to how the machine takes images, or can you just adjust some of the parameters?
Well, you're quite another good question. In principle, you're supposed to sample randomly, but that's crazy. It's not going to happen. So a big part of research is when do you not need random sampling? You know, when is deterministic sampling valid? I'm working on that. Lots of people are working on that. And the answer is, I mean, the theorem doesn't tell you all that, but unless you're really unlucky, it works. You know, deterministic stuff is okay. But the spiral sampling works, for example. But it's not proven, but it does work. Yeah. Yep.
So I've read a little bit about this stuff, and I understand more or less how it works if what you're sampling is in the Fourier space, but the images that you were denoising, that was sampled in like visual pixels.
Yeah, but the MRI stuff is sampled in Fourier space.
Right, but I was wondering, will you talk later about how you get it from a natural image?
You don't do this.
Pardon?
You do not do this.
Okay.
I mean, if you have a sparse signal, you cannot subsample it because you'll miss it. You've got to take some kind of transform. There has to be a matrix A over there. There is a matrix A which mixes everything up. Without that, it doesn't work. There are other ways of doing this kind of stuff. I mean, in painting and interpolation and whatnot. So you can do this stuff a lot faster by sampling. At UCLA, this is old stuff now. You can do it much faster. In principle, it was supposed to be hard to compute the image reconstruction. At UCLA, we developed new algorithms with split Bregman method that can be reconstructed quickly. And the word new is tricky here, very tricky. It was new to us, I'll tell you that. We were like Ramanujan. We derived all of optimization by ourselves. But it turned out that augmented Lagrangian methods, which have been around and done by friends of mine and also by Magnus Hestedes, have a big overlap with this stuff. So what we really found out was that the augmented Lagrangian method and variants of it are incredibly powerful for L1 and for total variation and for things homogeneous of degree 1. And they had been dismissed earlier. There's a great book by Boyd and Vandenberg on convex optimization. They don't mention augmented Lagrangian. So what we did was rederive it and find out how useful it was for this stuff and get even more famous. Okay. So that's what happened. And you have to set it up right and so on. But the reason this stuff works as well as it does is because we're applying it to L1 and TV, total variation, which means L1 of the gradient. If you apply this stuff to L2, which was done by people in fluid dynamics, it's not very useful, not very interesting, and has been dismissed. But L1, the sum of the absolute values rather than the sum squared, is what makes this stuff work. And that's where you get sparsity, that's where you get fast methods. And that's very surprising because L1 is not smooth, right? L1 looks like a V. L2 is this nice smooth stuff. So this is one time when you win because of non-smoothness. The world is a strange place. Okay, so we developed the split Bregman method, and my student just got an award for doing it, and it was one of the most popular papers, and it's not even new, amazingly enough. But it is new because we applied it to an interesting problem that had been around for a long time. Okay, and I'll talk about that. So you can do this, you can solve these optimization problems about as fast as a few FFTs, that same order of speed. And we'll get into that soon. And that makes life very interesting. And you can go pretty far with it. Okay. So here's a simple example. Here's the original image on the left. And conventional means conventional if you're retarded. But anyway, that's what they did. They would take the Fourier transform, whatever coefficient they didn't know, they would set equal to 0, they being people I won't name, and that's what you would get. So you set every coefficient you don't know equal to 0, you get terrible results. If you use a wavelet basis, and take this with a grain of salt because you can do better than that, that's what you get. But if you use total variation, which I will talk about soon, with 25% of the k-space data, it's almost exact. So that's a little triumph. That's not much of a medical image, but it's something. This is a little more realistic. This is a phantom image. There's the original image upper left. The upper right is 30% of k-space data. Left is 10 iteration. I missed the talk by Jorge Nosadal, my pal, but he was talking about augmented Lagrangian. He was negative, a little twerp. But I think what he was saying was that to get the smooth part right takes a while. But what this stuff does is find you the edges very, very, very quickly. If you're trying to find piecewise constant things with jump, or piecewise smooth things, you get the jumps almost immediately. Then the smooth stuff takes some time. And then you can switch to a second order method. But just using this nice, bare bones augmented Lagrangian, whatever you want to call it, stuff, you get something that looks good very quickly. It gets you all the significant features. And this is, and the subtitle of this meeting is feature detection or something. So you get it real fast with this stuff. So 30 iterations, you have it. If you go further, you have something better. But if you show that better thing to a radiologist, they will get very nervous because it looks better than the original. But it is better than the original because we did some denoising on top of it. But you can't show it to them because they get panicky. They like the noise. They're used to it. So that's what this stuff does. Okay? So both these images were acquired using 35% of k-space, which means Fourier transform. And on the right, we got the compressed sensing image. So the conclusion is that this allows MR images to be reconstructed from a small amount of k-space without sacrificing resolution or quality. You can speed it up 3 to 5 times. And if you don't believe me, go online, Google MRI, total variation, or MRI compressed sensing, and you will see about 150 papers in this stuff. So this is one example. This is one case when it penetrated the domain science very, very quickly, actually. Okay. So let's talk about the math involved. This is joint work with Wotow, who was here earlier this week. He's a smart guy. He's from Rice. And I'll try to explain why this stuff is so magical and how to do it. Yep.
Is there any concern about that denoising will get rid of a tumor or something like that?
Of course, yeah. So you got to be careful. But we find too many things anyway when we look at medical images. And there's a lot of overdiagnosis. But yeah, of course. I mean, this is not an exact science. And you have to trust your denoising algorithms. Yeah. Oh, of course, that's exactly what I was talking about with the radiologist. He wants the noise to be there because he's seen it for many, many years, and he knows what's noise, and he thinks he knows what's noise and what's not, you know, if it's not too bad. Well, yeah, that's a really important thing. Okay, so the Bregman methods, reviews and error cancellation results. These methods have the happy property that you can make mistakes, and they will forgive it. The world should be like this most of the time. You can do iteration and do it inexactly. But the limit solution will cancel out the errors, and it's only because of L1, which is amazing. Okay, here we go. So Bregman iteration has been unreasonable. By the way, Bregman is alive. He's like 85 years old, and he suddenly became famous. And he has published about 4 papers, but he invented the Bregman distance, which comes up a lot. Okay. There's better regularization quality over L1 and total variation, and fast and accurate iteration for L1. These are different points. We found out how useful it was when we were denoising. We improved our denoising by using Bregman iteration. But then one fine morning, Wotow called me up and said, hey, this stuff is unbelievably fast. And that's how it happened, to do L1 minimization. Okay, these are different points. So here's Bregman distance. The original model is minimize J of u plus F of u. F of u could be AU minus F quantity squared. I shouldn't call it F. Yeah, I can't call it F. It's AU minus W, some B squared or something like that. So, and J of u is a regularizer, which could be L2, God forbid, which is what it looked like on the left. That's u squared, or L1. Aha, that's good. That's a good one on the right. So on the left, you see L2. On the right, you see L1. And the Bregman distance, I have to shout because I'm leaving this thing, is this thing. You draw a tangent over here, you go down here, and you get this distance. That's the distance from U to UK. Can I take the microphone? Wow. I feel like a lounge singer or something. How do you do this? Oh, I'll be darned. Yay. Oh, holy mackerel. I'm very happy to be here. Okay. All right, so this is the Bregman distance. And you can see that for a strictly convex object, it's 0 only if a u equals uk. However, over here, the Bregman distance between this point and 0, any line which lies below the curve is an acceptable subgradient because this is not differentiable. This is a line lying below the curve, convex curve. So the Bregman distance between here and here could be 0. So if 2 elements have the same sign, then the distance, the Bregman distance, could be 0. And that's really crucial for the success of this L1 business. Anyway, what we want to do, instead of minimizing J of u plus F of u, we're going to minimize a sequence alpha times the Bregman distance plus F of u, where you have a solution of a previous iteration, and then you get the next one. Okay, that's what you do. And that, if the stars are aligned properly, will give you the minimizer of F of something which minimizes F of u, and which has very nice properties. Okay, so this gives you a constrained optimization. You lie in a space where, for example, if the minimum of F of u equals 0, which you can always normalize to make it so, you'll get something, you'll solve some kind of problem for which it is known that F is equal to 0. So for example, if the constraint was AU equals B, AU minus B squared, you'd solve the constraint in the limit. that AU equals B. Okay, so that's Bregman iteration. That is also augmented Lagrangian method in the special case when f is quadratic. Okay? It turns out that if you fool them out a little bit, and if the quantity f of u is AU minus b squared, then what you get is a sequence of minimizers which satisfy the same problem as the original one, except you replace b, which was what you started out with, by adding back the error. You add back bk minus auk plus 1. And when I did this, I stayed up for about 4 hours trying to make sure there was no mistaken sign. But no, it's right. You add back the error. You take the error and you add it back to what you got before. So you're solving the same kind of problem, exactly the same problem you solved before. So the numerics become simple, just with a different forcing term. So that's Bregman iteration for the special case of AU equals B. If you wish to minimize J of u such that AU equals B, this will do it if J is convex. And this will do it for any convex J. However, if J happens to be the L1 norm, it does it in an unbelievably fast way. Or if J happens to be something which is homogeneous of degree 1, like the integral of the absolute value of the gradient or something, then this is sensationally fast. Okay. And that's not a theorem, it's just my bragging. I mean, the only thing we can prove is that it converges in a finite number of steps. Yep.
What if J is not convex?
Now that's a very good question. The answer is it works sometimes. Yeah, amazingly, it works past where it should. So some people, instead of minimizing the L1 norm, are minimizing the LP norm with p less than 1. And they're getting pretty good results. But you got to be a little bit careful because it's not convex. But they do things to make it work. Yeah, so this thing works beyond where it should. But there's no theory yet. Okay. But not if it's L0. Then it's not going to work. Well, even there, people do crazy things and it almost works. Okay. But if you try to do this for LP where p is greater than 1, like L2, then this is not particularly fast at all. And it's a silly thing to do. Okay. It turns out. Okay. So here's some examples. Here is a very simple case. It's what do we have? The sparsity is pretty low. I don't know, we have about 10 or 15 non-zero elements there. The original system is sparse. If you take the original basis pursuit problem, you minimize the L1 norm of u plus this penalty term. Bregman says you take a sequence of these minimizers with bk that you get from adding back the error. And in doing that, instead of solving the original problem, which is this minimizer, you actually find out, you actually land in a set for which AU equals B. Okay. And you get this, you get the L1 minimum such that AU equals B. That's what you get. That's the theorem. Yeah, so the statement of the theorem basically is if you have a J of u over here and you do this and everything is okay, then you will minimize J of u such that AU equals B. That's what you will do. And that's better than minimizing the sum of mu times the L1 norm plus an error. Okay, so here, for example, if you do this with a fixed mu in front of it, and mu is too small, you don't do a great job. So you don't get back this nice, clean bunch of spikes, which is what you're looking for. Okay, you're slightly off. If you make mu a little bit bigger, 49, it's sparse, which is better. You get a lot more. Over here, on the left, you see lots of non-zeros. On the right, the non-zeros are going away, but the fitting is not great. You can see the amplitudes are off. If you make mu equals 150 or something, it doesn't really matter, and do a few iterations, you're on the money. You get everything more or less right, the amplitudes and everything. And this is not much slower than that because of this error stuff I'm going to talk about. Okay. So that's the deal, and I'll tell you how to solve these problems. This also improves the deblurring and denoising, and I haven't got time to go into that, but we thought we invented, I didn't even know what Bregman Distance was when we did that. We thought we invented this stuff in order to improve the performance of restoration algorithms, where you minimize total variation such that AU equals B. A could be a blurring kernel or something. And all I can do is brag and say this is better than the old version by doing this a few times. Okay. And you can see the error is smaller on the right. Okay, so for L1 you get sparser and better fitted signals. For total variation you get higher contrast. And the reason is you almost immediately capture the large edges, the large non-zero edges. And then when you minimize the Bregman distance, you don't penalize the edges, it turns out. Okay. Okay, very good. So you can apply this to constrained optimization problems. We did that. We proved finite conversion for L1, but we don't have a complexity estimate. The conversions could be e to the x to the n to the n to the, to the whatever to the n to the n, but the convergence is but the complexity is about 4 or 5 usually. It gets there very fast. Okay. And here are some theorems which are totally general, which have nothing to do with L1. And so they're misleading because they say everything is great. But it's only great if it's L1. I mean, because there's no rates over here. It just says that it's going to converge and you'll eventually get there if f is convex. Okay. But it also tells you when to stop. If you do this for denoising, which is not the main part of my talk, then the Bregman distance between what you're trying to get, the noise-free image, and what you have, the noise-free image, is diminishing as long as you're outside of a ball of some radius around the noisy image having to do with the variance of the noise. Okay, it's a little bit off. But anyway, this tells you when to stop when you're doing denoising this way. Okay. And there's a finite convergence for L1 result, which is nice to have, but it's just a mathematical thing because it doesn't give you a complexity estimate. But at least it's special to L1. Okay. But there's error cancellation, and this is the main part of what I'm going to talk about for a little bit. It's a happy result due to adding back. And it has to do with the fact that the L1 norm has some nice properties. So I'll skip some of these equations, but let's see if I can do this. Yeah, I'll skip that stuff. Here's a numerical example. A simple example, 500 entries, 25 non-zero, it's sparse. You have 250 projections, you have Gaussian random entries, you minimize the L1 norm of U such that AU equals B. You run Bregman. Now remember, when you run Bregman, you solve sub-problems. You minimize the L1, let me go back about 6 slides. When you solve the problem, you're minimizing constantly. You're minimizing that type of problem there in equation 1 where B replaced by BK. You're solving it over and over again. The fact of the matter is you don't have to solve it exactly. You can do one iteration of something and solve it very inexactly. But the error cancels and you land the right answer for the constrained optimization problem, even though the intermediate problems were solved badly. And that's because of L1. And that's why this stuff is so loved by the community. Let me get to it. Error cancellation, here we go. So you have these problems and you have to solve a whole bunch of intermediate problems, which are the form the L1 norm of U plus AU minus BK squared or something. So he solved them with a whole bunch of popular methods to solve them, at least 5 years ago roughly. These are the popular methods, there are others now. Anyway, he tried them all, but you solved them with tolerance 10 to the minus 6. And 500 entries, 25 non-zero sparse. You solve the problem. Each subproblem is inexactly solved. After one Bregman step, inexactly solved, you're within 10 to the minus 7 of the right answer of the constrained problem. After 2 iterations of this inexact solve, you're 10 to the minus 14. After 3 iterations, you're 10 to the minus 16, machine accuracy. So even though the intermediate problems were solved terribly, the error is forgiven. Because of the L1 business. And this definitely does not work for anything which is strictly convex, which means you have a round edge instead of a V at the bottom. And why it works we'll talk about now, actually. So it's amazing that error cancels. And there's a lot of mathematics left to be done to quantify this a little bit more. So classical results in augmented Lagrangian don't mention this. They require you to solve. Typically, when you do iterative procedure, you have to solve more exactly as you proceed down the line in your iteration. Here you can solve extremely badly and get worse or something, but nevertheless you'll get the answer in the limit. And the limit will be in a finite number of steps. Okay, the short answer is because the error cancels. Let me see, how do you do it? Let's see if I can do it. Okay, anyway, I'll get to that in a few minutes. There's lots of generalizations about this. You'll hear a lot about it in the next, I've covered like 1/9 of what I expected to cover in the next hour and 15 minutes, but anyway. There's lots of generalizations. There's logistic regression, which we'll show later, and support vector machine and things like that, which are more direct interest maybe to you guys. There's something called Linearized Bregman, which is a 3-line algorithm, which works pretty well. Instead of doing full Bregman, you replace AU minus B squared by the linear part, A transpose AUK minus B. There it is. That quantity over there. And then you add a penalty, U minus UK squared. And after you finish fooling around, the whole thing becomes 2 lines. There it is. So you can solve the problem, minimize the L1 norm of U such that AU equals B by this 2-line algorithm, I promise you. Delta shrink. What is shrink? Have I told you what shrink is? Yet. Shrink is something you learn to love very quickly in this world. Where the heck is shrink? I can't believe I got this far without mentioning it. Yikes. I may have to write on the blackboard. Shrink is crucial. So the only thing that makes this procedure nonlinear is the so-called shrink operator. Okay, I have to write nice and big and talk loud. But the basic idea is if you minimize the absolute value of x, that's the scalar function, plus let's say a constant over here, plus 1/2 x minus a squared. Minimize that over x. Scalar, decoupled, trivial, easy problem. The answer is soft thresholding. X is equal to shrink A comma C, which is equal to, and this looks like stuff that you may have seen in the learning part of this. Sorry?
How is this different than ISTA?
Completely different from ISTA. I've had this argument. It's a good question. ISTA would put over here UK. And that makes all the difference in the world. UK gives you the unconstrained problem, the penalty problem. VK gives you the constrained optimization problem. This is much better. It's different. Yeah, but I've had this. It's a good question. How do you know about this? Yeah. So, what he's asking about as a standard method for solving the unconstrained optimization problem. Minimize the L1 norm of U such that plus a constant, which would be in this case mu, times AU minus B squared. This is minimize the L1 norm of U such that AU equals B. Okay, and I'm lying actually. It's minimize the L1 norm of U plus a constant times U squared over L2 norm of U squared over 2, a teeny constant. This gives you actually lasso, as a matter of fact. And if you change the constant, you can get rid of the other constant. But anyway, this is not ISTA. This is more like this is the constrained optimization problem. And I'm going to show you why that's useful. But yeah, I'm glad you asked because people get confused about it. So one more time, ISTA does U over here. Okay. So on such little things, the world changes. Anyway, shrink is equal to A minus C if A is greater than C, 0 if the absolute value of A is less than or equal to C, and A plus C if A is less than minus C. Okay, that's shrink. So that's soft thresholding. If something is less than C in magnitude, it becomes 0. If it's bigger, you make it closer to 0 by C. Okay, so that's the only difference between L1 and L2, basically. But it's a big difference. You have to put that shrink in there. Okay. And there's lots of applications of this stuff. And there's lots of interpretations of this. And there's a nice paper by Wotow where he solves this very quickly. It turns out your question was a good one. You're minimizing, what you're actually doing is minimizing mu times the L1 norm of this plus 1 over 2 delta times this such that AU equals B. However, if delta is big enough, then this term goes away. Completely goes away. Not there. But it's not ISTA because ISTA would solve the sum of these two. Okay. Very good. Okay. And then there's alternating direction method of moments, which is split Bregman, which I will talk about later, for solving more complicated penalty problems. Instead of the L1 norm, you could have a total variation norm, which means replace the integral of u by integral of the absolute value of gradient of u, like that. Okay. And these things have been done before by Glowinski and Morocco in the 70s. Okay. But they didn't use it for L1. Okay. So let's talk about how L1 forgives and forgets errors. And this is kind of cute and very short. So what you're doing is minimizing the Bregman distance of u to u nu plus 1/2 u minus au minus f squared, and j is the L1 norm. And the 2 bar is L2. We are sloppy, making numerous errors. In fact, we're just randomly putting crazy stuff down. But suppose at the kth step of this procedure, we arrive at a UK such that the subgradient of P is the derivative of J, I haven't said that often enough, happens to lie in the range of A transpose. That's very important, and that's not completely trivial. So I like to sweep that under the rug because that's a harder condition. But the second condition is kind of something you can understand. There is a U star such that AU star equals F. So you're lying in the U star is in the feasible set that you're trying to solve for. And the Bregman distance between U star and UK equals 0. Suppose you happen to have that property for any Bregman distance, any convex J. Then the next iteration is the exact answer, period. Okay, so if you happen to get lucky and at the kth step your Bregman distance between anything which satisfies AU equals F and what you have is 0, and the other criterion, which is not so trivial, is satisfied, the next iteration will give you the exact answer. And a next iteration giving you the exact answer means you're finished in a finite number of steps. Now, first of all, if this was strictly convex, that would mean that U star equaled UK. Yeah, so you're not, so it's hard, but you don't get anything very good. If we're strictly convex, the Bregman distance is 0 if and only if U star equals UK. That's hard to happen. And that means you got to some unique minimum, which is unlikely, in your iteration. But if you do L1, that's pretty free. That criterion is nothing but the following. It means that for every component of U star, which is not 0, and it could be 1. Suppose what you're looking for is a 1 sparse quantity. So all you got to do is have one component of UK have the same sign as the component of U star that's not 0. And the next iteration gives you the answer. Pretty amazing. But I'm lying because you need that PK condition, which is a little harder to enforce. But anyway, this says that the signs SI, G, and S line up properly for the non-zero quantities of what you're looking for, or anything in the null space of AU minus F, the next iteration is the answer. And that's why this stuff is so blasted fast. Because if the signs line up, you're finished. You got there. It doesn't matter how terribly the intermediate iterates were, the errors all canceled out. And you got there. So for strictly convex J of U, that's not very interesting because that means that U star equals UK. And it doesn't tell you much. And the proof is real simple. UK plus 1 is the argmin of that sum. Both those quantities are non-negative. I haven't told you the Bregman distance is non-negative. You can see from that diagram, right? You're going to be non-negative if J is convex. So D of U UK is non-negative. AU minus F is 0, is non-negative. They're both 0 for U equals U star. So to minimize, it has to satisfy at least, it has to be 0, which means that AUK plus 1 equals F. Next iteration has that property. And the definition of Bregman distance, J of U minus J of UK plus 1 is blah, blah, blah. This inequality is valid. So J of UK plus 1 is less than or equal to this for any value of U satisfying AU equals F. You fool around a little bit. You need this P condition, AU minus AUK plus 1, FF 0. Okay, end of story. That's as technical as my talk will get. It's very simple. So the next iteration is the answer. If you land in a place where the signs are right, and it doesn't matter how you got there. So when people solve these problems using our glorious method, they don't solve the intermediate iterations to convergence. For example, when they do total variation, they do Gauss-Seidel for one sweep, if you know what I'm talking about. It converges to the total minimal total variation very quickly. Okay, so should I propagandize more? I'm almost ready to quit. Let me see. For the first hour. There's more about this stuff. There's one formula I like. If I can just do it without being too technical. The remarkable result is once, what this says, if you, I can't go through the details, but if you're minimizing the L1 norm, the problem I talked about before, the error at the kth iteration is the difference of the errors of the last two iterations. The other errors have canceled out, literally canceled out. They've disappeared. They're just the difference. Once the signs are stable and don't change, then the errors have canceled because of this L1 business. And you'll get rapid convergence. Here's another example. CT, tomography. This is the reconstruction of a cross-section of objects from its projections. The objective is to get a faithful image from limited projections. This is not a medical image. This is more annoying. This is a more serious application because we're talking about X-rays here, CTs, which will kill you, radiation. The idea is not just discomfort from MRs, but also minimize the exposure to radiation. So the CT dose is influenced by the number of projections and essentially the intensity, the fluence, magnitude. So you have missing data and whatnot, and I'll skip a lot of details. But anyway, by the time you finish doing all this, you want to recover an image when you know some measurements in the Fourier domain, which are taken along these angles, and some values in the wrong domain, and some assumptions on the image. And the idea is to get an image satisfying real and frequency constraints. And by the time you finish, you get this monster thing. You have some crazy set of linear equations, which one of my students has preconditioned in a nice way. When you solve this AU equal F business, it would be nice if A was a well-behaved matrix, right? So very often, it's a good idea to try to replace A by something better, by multiplying it by something preconditioning. And this learning business you heard about from Jan, what those magicians do, and the results are amazing, is replace A transpose A, the matrix we always get, by something which is better, faster, better behaved, and only approximate. And how that works is something I'm really interested in. But anyway, over here, what we have is AU equals F, and we precondition it. And the idea, very quickly, is this is related to compressed sensing. I'll go fast. You have missing data. Sorry. And you regularize. So basically, what you do is minimize the total variation, the integral of the absolute value of the gradient. There are other things you can minimize. Non-local total variation, which I haven't got time to get into. Or the sum of the wavelet coefficients, which I would have sneered at about a year ago. But I am since repenting. There's some beautiful stuff that's been done using redundant bases, multi-resolution bases, using framelets by grouping from Singapore and related, and they're really good results. They seem to beat TV. But they're not standard wavelets. They're a redundant basis, and I won't talk about that. Okay. Anyway, so one more time. You minimize total variation such that AU equals B. And here we go. I'll skip the details. Okay, and you also precondition the matrix A, which I won't describe. And you get good results. So here's some results. On the left is brand X, the old method that called filter back projection. Physicists love things like that because it has an exact formula. But these exact formulas usually involve dividing by 0, so you get oscillations. And on the right, this is what we get using ours with the same number of measurements. How do we know the one on the right is correct? Well, we do the one on the left with, well, first of all, let me go through the procedure to get it. You get there in like 3 iterations. That's what it looks like. And you can see things in principle with ours that you cannot see in the noisy filter back projection. And if you take more projections in the filter back projections, you seem to converge to ours with 8 times fewer projections. And this is old stuff. People have done better since then. This is probably a good time to take a break. Okay, so let me hold off for a half hour.